Hello, welcome back. I'm sure you are enjoying learning on embedded system design on ARM Cortex M4. If you haven't revised the previous sessions, please do go back and revise all the modules so you would be more familiar with using different peripherals and different registers associated with it, and you would be able to follow through. Today is day 26. You're going to learn about SPI. SPI is again a lengthy module, so I break that down to 2 days. So today is part 1. These are the sections you will learn today. So what is a SPI and how that is related with embedded system design, and how you're going to interface that with STM32F411, and then you're going to go and learn all about how the SPI works with the code. And today we will be learning to write the SPI GPIO initialization code, and we'll go from there. Before getting in, I would like to introduce myself. I am representing A2DG. It's a startup by Anbukarasu brothers. My brother Alex and myself Arul in 2023. Both of us gathered over 20 plus years industry experience, and we would really like to put it out there so that it would be beneficial for you to shape you into a better professional. Our mission is to convey our knowledge to at least 100,000 future professionals through our online courses. And the main advantage is you can study from wherever you are, and that's really good about that. About me, I'm Arul P. Anbukarasu. You can call me as Arul or API, as persistent as I would like to be to share my knowledge and experience with you all. I have 20 plus years of experience working in various industries in Australia, Italy, Singapore and India, majoring on these renewable energy sector on solar and wind power conversions, power systems that related to lead acid batteries, network embedded systems that connected to ATMs, TCRs and point of sale machines, banking automation systems and smart parking operations. And my expertise lies in these three areas of embedded systems, VLSI and project management. I have a small announcement to make. I categorized into two different categories: the YouTube viewers and the internship professionals. In order to be eligible to get a free certificate, you have to attend at least 28 video sessions and watch it through. At the end of each and every session, there will be an attendance link. Please to click on that and fill your details and send it to us, and that will count for your attendance. Due to the regulations of YouTube, the videos can't live there forever in our channel on A2DG site channel. It will be removed after 2 or 3 days. So in case if you have missed out on one session, if you want to go back to do a recap, unfortunately you miss out. That's why I really encourage you and advise you and recommend you to join one of our internship program that acquires you to get an internship certificate, and that's worth a lot, because when you land into that interview panel or after you got that first job, when you work with the senior engineers, they think this 30-day journey that you already put through, that you learned all the fundamentals and you had your hands on creating projects and verifying that projects worked with the hardware, everything, it all counts, because they don't have to teach you much, so you can just start from day one and be more productive with the team. Not only that, you will get your own login to log into our learning management system portal to go and check on each and every session. So once you finish, just click on complete. That will count for your attendance. On top of that, you will get unlimited access to course contents. That includes all the PDF materials, the source codes, the data sheet, reference manual, whatever you need for the series, for this course. And also unlimited access to all the course videos. You could pause the video and you can go and do something else, come back and watch it, or if you want to go back and revise something else, you can do so. It's yours. If you get stuck somewhere in the middle, please do contact our backend team, and they are a friendly team and they would be able to help you to make your journey go smoother along. So shall we get in to learn and see what the day falls out for us? I'm sure you are keen as I am. So let's get in and learn. Shall we? SPY. As you know, you have gone through this numerous times in your engineering degree, and you might have also heard from a lot of people out there, from the industrialists. So the SPI is abbreviated for Serial Peripheral Interface. The SPI bus allows, it is also another communication protocol. So the SPI bus allows the communication between one master device and one or more slave devices. So that is the basic difference between the other communication protocol that we learned, I2C. I2C can have multiple masters and multiple slaves, whereas in SPI it can have only one main master device, and it can have either one single slave device or multiple slave devices. And SPI works on a 4-wire configuration. So you need a serial clock, MOSI, MISO, and GPIO chip select. MOSI stands for master out slave in, MISO stands for master in slave out, and the chip select, like if you want to send the address from master to the slave devices, it only talks to the slave devices through the chip select, the slave select, as in this picture. So the slave select, it is nothing but the GPIO pin. So to control, and as you know, the slave can be interfaced with sensors like accelerometer or temperature sensor, whatever the case may be, or EPROMs, or even the memory locations. So the when it wants to communicate, so it will communicate from clock to clock, the connection is, and only the chip select controls the master, and that is connected to a GPIO. So this is the basic SPI definition. The slave device is a precision data converter, whereas the master device is the microcontroller. So you're going to interface that to the microcontroller with some measurements. So in this SPI series, you're also going to interface that with accelerometer, but you will cover that and you will learn that in the next part. But today we're going to learn the basics of SPI and all the registers associated with it, and then you will start to learn to code the initialization code. Also, when we talk about communication protocols, there are two communication, as you may remember, serial and parallel. When you compare between serial and parallel, SPI is a serial communication protocol, whereas because how you can compare with the parallel is, the parallel is much faster because at one time you can send 1 byte, so that means 8 bits can be sent in one instance, but it requires 8 different data lines, whereas in SPI it is in a serial communication, so you can send 1 bit at a time, and you can do so by just 1 line, so you don't need 8 lines. So that's the major benefit. But being it's sent 1 bit at a time, occasionally you may feel that this could be slower compared to the I2C. So that is the basic difference between the serial and parallel. Now a small comparison with the SPI and the I2C compared to the USB 3s and 2s. As you can see, SPI is a synchronous serial, and the maximum device or the distance that it can connect up to is 10 feet, and the maximum speed is nothing but the frequency of the internal clock, the system clock, divided by 2. That's how the speed of transition of data, right? And in our program we're going to use BRR register, and that's what determines the baud rate. And comparatively, when you see that into the I2C, it is also a synchronous serial, but the maximum distance is 18 feet, and it can work on high speed mode as well. Whereas the RS-232, 485 are in asynchronous, and they can shoot for long distance. Likewise with the Ethernet also, it can be connected to long distances, and its maximum speed is 10G. The USB 3 is simplex serial, and the USB 2 is half duplex type, as You are aware already all those terminologies of full duplex and half duplex and simplex. And Unit 3, USB 3G is connected, the maximum speed converts to 5G, and USB 2 can run up to 12 megabits per second. So these are all some of the examples that compare with the SPIs. So in other words, I2C and SPI is used for short distance communications, whereas the other protocols are used for long distance communications. So to summarize that, SPI and I2C, these peripherals communicate over the TTL logic, signaling in the voltage range of 0 to 5 volts, whereas protocols like CAN and RS485 communicate over a differential signaling, and that is well over 10 volts. That's the major difference. So that's why the SPI and I2C are short distance communication interfaces. So that's a summary. Now let's go into seeing about the SPI voltage levels. As you know, the voltage levels, whenever there is a waveform, high voltage is 1, that means it's on a on state, and if it is off, that means 0, the voltage is on the off state. So this is how the serial data is converted. And basically all the master and the slave should be running on the same voltage, but in some devices, if the master has to be operated on a separate voltage level and the slave has to be operated on a separate voltage level, then you need to have a voltage level translator which translates and connects to the required voltage levels to the devices. So if the master and the slave operate on different supply voltages, then with the use of voltage level translator, you can accompany that. And also, if you refer the data sheets, the voltage levels will be defined there. Between ground and VDD, you will have the voltage output high and voltage output low values, and the voltage input low and voltage input high values will be designed and defined in the data sheet. So please do follow the data sheet. It is a must, and you need to be familiar with all these terms. Now let's get into talk about the SPI a little bit in detail. As we just learned, SPI, the master controls the slave select and the serial clock. The SPI can have only one master but can have multiple slave devices. If it has 2 or more slave devices, that means it will have furthermore chip select lines. So only one can be connected at one time. And each slave has a slave select for independent control as well. And the data in here will be transmitted from master to slave or slave to master. That's the full duplex communication. Now let's see what is the slave select can be done. Slave select, this is the one, selects the slave device for communications. It is often considered as active low. So as you can see, there is a bar over SS, slave select, and this sometimes called by other names known as SL or CS bar, chip select bar, or chip select sync. In Texas Instruments you would see lowercase n and SS or SS hash. So commonly lot of data sheets you will see CS bar, that means it's active low or sync low, and it is used for the data converters, and you would see that in the TI devices that's used for data conversions. So that's the slave select bit pin. Next is the serial clock, which is this. The serial clock is the one that synchronizes all the clock and starts to do the data transmission between the master and the slave. And the serial clock originates from one master, and it can connect to the shared slaves. And also clock can be idle high or low, and data is clocked in either the rising edge or the falling edge of the clock. Also, other denotion, it can be sometimes called as SEK, and that's what the accelerometer has, SEK. Next is the master out slave pin. What is this? So this pin is an output pin. So it sends the output from the master, send the data to the slave, and connects to the MOSI pin. So it can be also connected to various slave devices as well. And in Texas Instruments and some other microcontrollers, you will hear this as in different names as master, or from the slave device it's called as the slave device in, device input, device in, and SI from the master device. It's called as data out, D out, and serial out. That's serial in, serial out. So commonly labeled as data in T1 data converters. Next one is the master in, slave out. Here the difference is the output from the slave device used to send to the data to the master. So that's the difference. MOSI is the other way. MOSI sends data from master to slave. MISO sends data from slave to master. And it can also be shared with other slave devices. Slave output becomes high impedance when SS is not selected. So when you don't select this, then it can result in high impedance state. And also this is known from other names. From the slave device is SDO, DO, DOut, SO, and from the master device this can be also written as SDI, DI, DIN. So generally in the TI devices you would declare this as DOut converters, data converters. So now let's go into learn about the clock polarity, C pole. As in this timing diagram, the chip select, as you know, it's always active low. So when you set the C pole as 0, that means the leading edge is rising edge, trailing edge is falling edge. So the other names for the leading edge is called the rising edge. The other name for falling edge is called the trailing edge. And if the serial clock is set, or if the serial clock is low, that's when the clock polarity is set to 0. But in the other case, when the serial clock is 1, then the clock polarity is set as 1. This means the reverse. Leading edge is falling edge and the rising edge is trailing edge. So it's the other way around. And data is read from left to right. So for each clock pulse, the leading edge is the first edge of the pulse, the leading edge. If it is clock polarity 0, then the leading edge is the rising edge. If the clock polarity equals 1, then the leading edge is the falling edge, or the falling edge. And the trailing edge is always the second pulse, the second pulse. So that's what the clock polarity is. That's what we just learned about the protocol bus modes, the SPI protocol bus modes. On C polarity, if it is 0, that indicates sampling on the first edge. If clock polarity is set to 1, that indicates the second edge of the sampling. Next is the clock phase. When the clock phase, what clock phase is, when the data is clocked, when C pole is 1 or C pole equal to 1, so 0 or 1, and the phase how it is generated and how it is linked. So in this case, in this timing diagram, when the CPHA is 0, that means data is clocked in all the leading edges, as you can see, data. So whatever this shows in the rising edge, that will fall to the CPHA 0. In this case, data is set when SS falls low or at the previous trailing edge of serial clock. So for C pole of 0, this is the rising edge, and CPOL of 1, this is the same one, this will be the falling edge. So that's the clock phase 0. In clock phase 1, it's the other way around. Data is clocked on the trailing edge, meaning if CPOL 1 equals, if clock polarity equals 0, then this is in the falling edge. If clock polarity equals 1, then this is the rising edge. It's the other way around. So whatever the value there, and that's captures in the C clock phase 1. SPI mode has 4 different mode numbers, and we're going to use 0, 1 or 1, 0, anything that you wish. When you write polarity, clock polarity and the phase in 0, 0 mode, that means it's a 0 mode. 1 mode is clock polarity 0 and clock phase is 1. If clock polarity is 1 and clock phase is 0, then that's a SPI 2 mode. For 3 mode, both are 1. In this example, it's shown for 0, 1. So CPOL equal 1, so that means on the trailing edge, clock phase 1 captures whatever data in there. So this is the mode numbers. And the protocol of CPOL and CPI, it's just an explanation from the continuation from the previous slide. If the clock polarity is set to 0, then the active state of clock is 1. The idle state of clock is 0. You can either write CPHI is 0 or CPHI is 1. If it is clock phase is 0, the data is captured on the rising edge and data is output on the falling edge. But if it is clock phase 1, data is captured on the falling edge and data output is on the rising edge. And the difference with the clock polarity is 1, then the active state of the clock is set to 0, the idle state becomes 1. In this case, it's the reverse of this condition. On the clock phase is 0, data is captured on the falling edge and the data out is rising edge. Clock phase is 1, data is captured on the rising edge and data output is on the falling edge. This is just a comparison between a single slave and a multi-slave. As you know, MOSI can be written also and denoted also as serial data in, serial data out. MISO is for serial data out, and chip select, slave select can be also used as a chip enable pin as well. So this is a single master single slave device, and this is the single master multiple slave device connection. So this is how it's connected. So the clock will be connected commonly from this, and MOSI will be connected to slave MOSI, and from the MISO it will be connected to the MISO, and you will have separate chip select lines, and everything is independent. So every line has to be controlled and connected to the following chip select line. So this is how it's connected. Yeah. And controlling about the multiple slaves, each device has an independent slave and it will connect through this chip slave select. S-clock, MISO and MOSI are each shared between the devices, so you can share that, but the chip select will have its own independent slave select. If device is not selected, MISO will go into high impedance mode, so it has to be in one of the select mode. And the controlling can also be done in another method called daisy chain. Daisy chain is nothing but the serial clock is connected as it is. The MOSI is connected to MOSI, but look at this MISO. The first MISO is connected to the second MOSI of the slave device. The second MISO is connected to the third MOSI of the slave device. And the third MISO is connected to the master. So this is like in a loop. That's why it's a daisy chain. It's almost everywhere. You will hear it in the industry. Daisy chain not only also relates to microcontroller, even if you do some group activity and if there is a link between one activity to the other, then that's also considered as a daisy chain. But again, you need to check with the data sheet and the particular microcontroller to see whether that SPI supports a daisy chain. If not, you need to go for the standard control measure the previous connections like this. And the meso is connected to the meso. So daisy chain is first this connection, and then the meso is connected to this meso. Now let's find out how it works with the protocol. First, the transaction is started by enabling the system clock. With the clock generator, it enables the clock. Then the SPI works with the shift register. The master sets the chip select line to 0, and then two registers of the same size are involved in the transmission, one in the master and one in the slave. Data is usually shifted out with the most significant bit first. Always the MSC goes out first. So for example, I'll explain in the next slide. And then at the same time, data from the slave is transmitted. Being a full duplex, it can also transmit back through via the shift register. It transmits back, and that's how the operation conducts. So if more data to be exchanged, the shift registers will be reloaded and the process of exchange will start again. When no more data is transmitted, the master will simply stop and toggle between the clock and the deselect slave line. So this is how the protocol works. And this is the one good explanation. First, you are sending the serial clock, you're generating the serial clock, then the shift register start its conversion. And the first conversion, you're going to send this B0 to here. So you already shifted the A0 to here. So likewise, you need to shift everything, A0, A1, A2, A3, A4, A2, A4, A7 in 8 iterations. So now the MOSI and the meso, so both the shift, using the shift registers, both the bits are transferred. So it's a full duplex. So this is how it is done. So when you transmit one data, the other one gets filled back. So I'll go here. This is the start. So now you're transmitting A0, and watch this. B0 will come here. When A1 goes here, then B1 will come here. Likewise, when A4 goes here, then B4 will go here. So nothing is left empty or vacant. So this is the SPI protocol. This is how it works. And again, we already heard about the full duplex. Full duplex stands for you can transmit and receive at the same time, and that's the full duplex configuration. And always the most significant bit is transmitted first or send data first, and then the LSB bit. The half duplex, you can determine whether it is a transmit or a receive. There is another method called simplex communication. In this, you can either only transmit or only receive. It can't be either or. It can be set just as a transmit or a receive. So that's a simplex communication. In the data sheet, you need to first go through the chip select and the D in and D out and see where they are all connected. So the timing diagram with D in and D out. A timing diagram shows us whole specifications and the relationships between the digital lines. Violating a timing specification can cause a failure because it may have runout error, timeout error, and this is how the SPI communication. The chip select has to be low and the clock is generated. Depends on the clock polarity and clock phase. The data in and data out is connected. So just to transfer 0 cross D2 on a MOSI and 0 cross 75 on the MOSI, this is how it's when chip select is active low on the rising edge. This is how the data gets transferred. So the binary value is 1101 0010, and that's nothing but 0 cross D2. And here the MOSI, the binary value is 0011 0101, and that's 0 cross 75. This is how being at the rising edge configuration. Now let's get into the timing. The timing, it has three different timing in SPI. The first is the setup time, then there is a hold time and a propagation delay. The SPI timing is nothing but is the minimum time required before the clocking edge starts, for which the data must be stable. So there must be some time set before the clock generated, so it will have some time to merge through to be latched correctly. So this is what it shows in the diagram, in the timing diagram, D in and D out. So this dotted lines, it's called the setup time. The state of D init is read into the device at the rising edge of the serial clock. So this is the setup time. Next one is the SPI switching, hold time and propagation delay, and these three pins are involved: serial clock, D in and D out. So that means in the serial clock, when the hold time is the minimum time required, after the clocking edge happens, then there is some time that's required for the data to be transmitted, to be stable, so that extra time needing to adjust the clock, and that's what the hold time. So it has to hold or pause for a while to get that data. And then there is the propagation delay. SPI communication example. So this is an example with the chip select. When considering the S clock is in the low and data is clocked on the falling edge. Remember, if it is on low, then it is on the falling edge. And we're going to send D in as 81C3H to the device. And when you use that for every clock generation, you need to generate that. And the D out is nothing but whatever it gets on the falling edge, and that comes through. Here it's positive on state, so that's 1. Here it's on, but the data input is 0, but doesn't matter. This is 1, so this is also 1. This is 1. This is 1. But here the transition changes to 0, then 0, so 1. Likewise it's connected, and then this is the binary value for the D input, and this is the hexadecimal value. So this is how through SPI the data is sent and read. These are all some of the advantages and disadvantages. Advantages of the SPI is it's faster than asynchronous serial communication. The receive hardware can be simple used by shift registers, and it supports multiple peripherals like multiple slave devices. Whereas being data sent in one single line compared to the other communication mode, sometimes this can be defined as a slow moving SPI. So that's a small minor disadvantage. The controller must control all communication peripherals and can't talk directly to each other. That's another drawback. It usually requires a separate chip select line, so therefore you need extra lines to connect to each and every slave device. So these are all these disadvantages. Now let's see briefly or elaborately into where the SPI in STM32F411 is. STM32F411 slave select pin management. When you want the device to act as a slave mode, in the slave mode, remember the NSS work as a standard chip select in input and lets the slave communication with the master. But when a device is configured and to be used as a master mode, in the master mode, NSS can be used either as an output or an input. It depends. Being master has that extra luxury being used as an input or output, but in the slave mode, chip select can always be set as an input. So as an input can prevent multi-master bus collision. So that's the main reason, a master code to avoid the bus collision. So it has to be used as an output in that. And as an output, it can drive a slave signal of a single slave. These are all the SPI types of slave management. and the slave management is controlled through a software. In this configuration, slave select information is driven through this bit value, and the SPI is controlled by the control register. And the NSS pin is free from other applications use. So the hardware or the software select management can set using the SSM bit in the control register. That's the slave select management bit. SSM bit is slave select management bit. And this is the typical functional block diagram of the SPI. Because both master and slave needs its own registers, so it will have a separate shift registers, and it will have its own RX buffer and the TX buffer. So that's how it's communicated. So always remember MSB first and LSB. The serial clock is generated and fed to the baud rate generator. This determines the frequency, the speed of the controller, and then the active low is connected to the master control logic. And with the communication control, this can be controlled over the control register 2, which has the TXC bit and the RXC receive not ready bit. And with the status register, it also has a TXC, and control register 2 is all used for the interrupts. Serial registers is all used for these bits, TXC, RXNE. And through this baud rate generator between bits 2 to 0, you can set the value. You will see that in the program. And control register 1 will have the slave select management, and it will have the DFF. That's also main data frame format, because that's how the data is transferred through this bit, and RX only. So if you go to the functional block diagram, you can see the SPI peripheral bus connections. So you need to enable, okay, in this example we're going to connect and use SPI1. SPI1 is connected to APB2 peripheral bus, and we also going to use GPIO-A bit. So we need to enable GPIO-A enable and the SPI enable, both clock access. So this is how the frequency is calculated. As you know, the high speed internal line and the high speed external line and the phase lock loop all integrates to a mux and comes out as 16 megahertz. It put through to a bus prescaler with the 50 hertz APB1 cycle, the peripheral bus. As you know, the internal system clock is 16 megahertz, and if it comes to the SPI, it comes out as a minimum prescaler by 2, so you get as the 8 megahertz. So we're going to use the 8 megahertz value. And now let's go in to see some of the control registers, all the registers that's going to be associated and will be using in our program. And this is the control register 1. In this we'll be using the clock phase, clock polarity bit, the master bit, and this is the baud rate generator bit between bits 5, 4, 3, and then the slave select, internal slave select, and this is the slave select management or software slave management, I should say, and the data frame format and RX only. The others we are not going to use in this one, but we'll be using bit 0, 1, 2, 3, 4, 5 and 7, 8, 9 and 11. These are all the bits we'll be using in the program. And the control register 2 is used for interrupts. So if you want to generate any interrupts, then CR2 is used. And you can also check with the status register with these 3 mode: TXC, RXNE and busy mode, which is bit 1, 0 and 7th bit is the busy bit. So these 3 are used to check the status. And then the data register, that's where the data gets read from. So you need to use bit 1 and bit 0 and then bit 7, because these 3 are the status register, SR SR1, so you need to use 107, the SPI register. And then there is also the SPI CRC register and the SPI transmit CRC register and the SPI I2SC function. This is the registers. The I2C prescaler register. This is where the prescale values are calculated. And now let's go into the schematic. This is the schematic of the ADXL 345. We're going to use port A for this program. So the SDO is connected to MISO as PA6. The serial clock is connected to PA5. The serial data SDA MOSI is connected to PA7. And the chip select can be any GPIO. So we are going to use PA9 as the chip select. And this is the pin configuration details. I already connected the hardware and it's ready to go. So please to purchase the hardware and practice with the hardware. Now you learned all the schematics and all the basics and everything in theory. So please go and have a couple of minutes break. When you come back, let's learn to write the SPI GPIO initialization code from scratch, and I'll show you line by line. So I'll see you back in a couple of minutes. So go and enjoy that break. I'll see you back shortly. Hello and welcome back. I'm sure you would have enjoyed that mini break. So this is where we finish. So let's go now and learn the learn to program from line 1. So I will minimize this, and I already opened IDE, and in the desktop I already went and created a folder called SPI, and then I created another folder called target. And as you know, we're going to use the header files, the built-in header files today as well to program all the registers. So you need to download this. As if you remember from the LCD, we went to STM32 site and we downloaded from there. If not, please follow that video, and there is an explanation about where to go to find this, and then extract these files and leave it here, because you need to include 2 paths and 1 symbol declaration. So that's why you need this extracted here. So click on the target and then highlight this, because we're going to work in this workspace. So copy that, go to IDE, and then go to File, switch workspace, and click on Other, and then paste it here. Make sure the SPI target is related to this, and then click on Launch. So this will entirely start everything from a new file, new perspective. So I'll connect the hardware again. I just disconnected. The IDE is opening in the background. When it is ready, then I'll show you shortly which one belong. Just wait for me, please. It's still loading. I will move myself so you can see the full IDE. So just one sec. We lost the connection. Just okay, welcome back. I will run through what I did. So I opened a folder in the desktop and named as Spy, and I opened another folder called Target, and I went open the target and I highlighted this, copied here, went to File on the IDE. I change the workspace, go to switch workspace, click on Other, and make sure you are working on the same the spy target, and then click on Launch. Will bring you this screen. So we don't need the information center. I'll close this. And then you need to start a new project. File, new, STM32 project. STM32 project. So this will allow, and it will take some time to select the board, because we are doing scratch from the workspace, so sometimes it takes a while to do that. So we got to patiently wait until the system allows us to do, because the blue circle is still going on. So just bear with me. Oh, there it is. So first we need to include the two data parts from CMSys and the core M4, then the symbol. Initially it has to check a lot of things, so that's why it takes a long time. So there it is, board selector. We're going to use Nucleo F411, so please type that and get the board and select it. Select that board, and then next, and the project name is day 26 SPY part 1, and then choose empty for the targeted project type, and then click finish. We're going to use the internal built-in header files. So for that you need to do those 3 steps, if you remember. I'll go to source, open the main C, and I'll remove all the default lines, and I will build the project. So that will give us I'll zoom in a bit. Window editor, zoom in so you can see better. Window, yeah, and then I'll delete all the pre-written programs. As you know, this is for the reference, so I'll leave it as it is there. Now I'll just go and simply build, so that the ELF file will start to generate first, and also it will check for any errors. As you can see, there is a 19% build. So it takes a while, and the .elf file is generated, which is the one we want. 0 errors, 0 warnings. In order to use the built-in header file, you need to do 3 things. So go back to the target, the SPY folder, and go to this STM cube extraction. You have to first go to drivers, the first step, drivers, then go to CMSys, and then go to device, go to STM32F, and include this. Make sure the STM32F411xe.h header file is in here. So copy this path, copy, come here to the project name, right click on the project name, go to properties. In the properties, select C, C++ build. In C, C++ build, go to settings. In the settings, go to MCU GCC compiler. In the MCU GCC compiler, click on include paths. And in the include paths, click on the add icon, that's a directory. So paste the link and then click OK. So the first step is connected. So the next one, you need to also copy the device path core M4. To do that, just go to device. It will be inside drivers, CMSys, under core, and then include. You need this core CM4 header file. So copy this path and also do the same. So go to the project name, do a right click and go to properties. Okay, I'll apply this. I'll show you step by step. Yes. apply and close. Okay, so again now you go to project name, right click, properties, C++ build, settings, MCU GCC compiler, include paths, add the second path. Yeah. Okay, so the two paths are included, then apply yes to it, and then apply and close. So now you link the paths, and now you can include this line to include the built-in header file. I'll show you, there will be an error. So being a built-in header file, it has to be written in quotes, double quotes, stm32f4xx.h. So I'll just go and save. You will get an error because we haven't declared the project. We haven't declared the symbol. So you'll get these three errors. This nothing but it's showing that the Cortex M4, these are all connected, but it's missing a device symbol. So to do that, just simply select this, right click, open declaration, and then go and find that lab, the symbol STM32F411RE, this one. So we need this. XC, copy this, come here, right click on the project name, go to properties, go to C++ build, go to settings, go to MCU GCC compiler. This time click on the preprocessor and watch here, it is not on the list, define symbols list. Click on add, define symbols, you just paste that symbol STM32F411XE, it's copied and paste it, apply and say yes, and then apply and close. And you don't need this file, so now you just go here, right click and build the project. Now all the necessary paths and the symbol is declared, so you won't get any error. The next step, we'll go and start to write the code. Okay, 0 0, that's really good. Okay, the first step is we're going to write the GPIO code. So for that, first you got to define the function SPI underscore GPIO init, initialization today of void. So I did declare that, so copy, and we're going to write the function. Okay, so this time I will go to the data sheet. I will also show, that's the ADXL345, which I will show you later. This is the alternate function. We're going to use pi1, so we're going to use PA5 for serial SPI serial clock. PA6 is used for SPI1 MESA. PA7 is used for SPI1 MOSI, and we're going to use the GPIO for the chip select, so we're going to use PA9. And if you check on the alternate function, it's AF05, but I'll show you the register that we need to work on. So we need to enable the clock access for first the GPIO register. So first GPIO RCC. First you need to enable the clocks, so I'll go to the RCC register. First you need to enable AHB1 ENR So we're going to use GPIO A, that is the port A, so you need to enable the port 0 as 1. And also I2C1 is connected to peripheral bus 2, so you need to enable APB2ENR as well. APB2ENR we are going to use Pi1 enable, so I need to enable the bit 12. So these two are the first steps. First, clock access to GPIO A and SPI1. To do that, you need to do RCC AHB1 ENR register, and you simply R that with GPIO A enable. So this is the one. Before doing that, you need to declare the macros. So macros hash define GPIO A enable. GPIO A enable is nothing but the first pin, so 1 U of bit 0 and the 12th bit for SPI 1. So hash define define SPI 1 enable, and this will be the 12th bit, and U. Okay, so that's not I, it's 1 U. Okay, so next step, I'll just simply copy this. That's a clock access for GPIO A. This is clock access to SPI 1. So this is APB2 ENR. APB2 ENR, and this is, you have to copy SPI 1 enable. Okay, then this next step is you need to set the those pins for all those 4 pins. So you need to set the modder register for all those pins. So next step, set output modder register for PA5, PA6 and PA7. So we're going to use the GPIO A. So again, go back to the data sheet. Data sheet. No, sorry, the reference manual, and go to output data mode register. So go to GPIO modder register, which is this one. So we're going to use PA5, which is, that's PA0, 1, 2, 3, 4, 5. We're going to use this as the alternate function mode. So to do that, you need to set 1, 0. You need to write 1, 0 in all those bits. So 0, 1, 2, 3, 4, 5. So you need to write bit 11 as 1 and bit 10 as 0, and this is PA6, 13 as 1 and 12 as 0, and PA7 we're going to also use bit 15 will be 1, bit 14 will be 0. So that's what we're going to write now. So GPIOA model register PA5. We are going to use the PA5. So bit 10 to write 0, you need to AND that with a negate and then declare that pin. So this is PA5 bit 10. I'll copy this and also use it for the bit 11 has to be 1. Bit 11 has to be 1. To write as 1, you just need to simply R. That means it's 1, PA bit as 1. So likewise, you got to do for port A6 and port A7. Port A5, this is port A5. Port A5. Copy this again. You're going to do for 3 times. This is 6. This is 7. This will be 12 and this will be 13 and this will be 14 and this will be 15th bit and this will be PA7 bit 15 bit 14. This is bit 13 PA6. This is PA6 and this will be bit 12. So after this we need to set the chip select output. So for that, set PA9 as chip select and as output. So as you know, as output, so again go back to the registers. If you want to use the output model as just as an output, then you got to write as 0 1. So this is PA 0 1 2 3 4 5 6 7 8 9. So you need to write bit 19 as 1, bit 18 as 0. That's what we're going to do. 0 1. So bit 19 0, bit 18 as 1. So I'll just copy these 2 lines. We need that lines. Come here and paste it. This is PA9 bit 18 bit 18. This will be bit 19 PA9. So this will be 18 and this will be 19. So I'll just Control X, Control V, I'm just organizing, sorry. Okay, so the chip select, slave select is done. So the next step after this is to define the alternate function register. So you need to set all this to SPY1. SPY1 we are using PA5, 6, 7 and PA9. So the corresponding alternate function from the table is AF05. So that's what we're going to do. Set AFR with SPI 1 registers as 5, 6, 7, which will be on the AFR low registers, and the value will be AFR 05. That is, you need to write 0101 on all these alternate function registers. So to do that, I will start writing 1, then I'll show you GPIOA AFR of 0, and you need to set the bit as 1 U 20. And I will copy this, Control C, Control V, and this will be AFR register, Control C, Control V, AFR register, and this will be 21. Okay, you need these two again for bit 22 and 23. It will be 22, 23. So we are writing bit 20 as 1, bit 21 as 0, bit 22 as 1, bit 23 as 0. So that's what we have written. If we go here, this is the port mode register. If you keep going to alternate function register, pull up data register, alternate function low register, you need to go alternate function low register, because we're going to use, this is 0, 1, 2, 3, 4, 5. So the bits 23, 22, 21, 20, you need to set it for AF5, because from the alternate function table that's linked to AF05. We go to the data sheet, alternate function 05 is linked to SPI1 PA5. We're going to use clock, meso and mosi. It's all linked to AF05, so that's why we are doing. So to write AF05, you need to use, that's 5, 6 and 7. So you need to write 0101 on this 4 bits, and again this 0101 on this 4 bits. So AF5 value is 0101. That's what I have written here. I'll simply go and copy this and I'll paste it twice. Copy. And 23, so this will be 24, 25, 26 and 27, and this will be 28. As I know, it's a 32 bit. 29, so will be 30, and this will be 31. Okay. So now we need to set we set the output data, so we don't need the GPIO 31. Okay, this is all the config we need. Yeah, so after config you also need, after init you also need a config register. You need to set all those configurations, so copy another one. This time it will be SPI config. SPI config function. Copy. Okay, in the config, then I will just quickly check for any errors at this stage, so we can check as we go along. So right click, build the project. It's building to 23%. Okay, 0 errors, 0 warnings, which is always good sign. So now let's go and define all the configuration bits. The first step will be, you need to use the status registers and the control registers one. So go here, reference manual, you need to go to SPI CR1. So I'll click on the contents, scroll to SPI, that's a GPIO, ADC, RTC, I2C, SPI, and then SPI registers, you need to go to SPI control register. So you need to set all this configuration. Clock phase, you need to set clock polarity, bit to master, and the bit rate. We're going to use 4001, that is frequency of the peripheral clock divided by 4. We're going to set this into the speed, so we will be setting bits 5 to 3 as this value 001. So bit 5 will be 0, bit 4 will be 0, bit 3 as 1 to use that. And then the other bits called DFF, SSM, SSI, the LSB first bit, all this will be configured one by one now. So we're going to configure the control register. So first set the FP clock 4. To do that, you need to do SPI 1 control register 1, and just simply R that with 3 times, because we're going to set the F clock by 4. That means the bit rate, baud rate generator 543, so 001. So that's what I'm writing. I have just written bit 3 as 1, so now I need to go and write bit 4 and 5 as 0 for the clock generation. So I'll simply copy this and modify this. This will be bit 4, and to write as 0 you need to negate, and you need to simply AND that. That's 4, and we also need a 5th baud rate. So 3, 4, 5. Okay, so then you need to set the clock polarity as 1 and the clock phase as 1. Next step, set cpol equals 1 and cphi equals 1. So that means bit 0 and 1. If you go back to the register, you need to set these two, 1 and 0. 0 and 1. So we need to set, I'll just copy this twice, and then I will change this to 0 and 1. Okay, then the next step is configure the SPI in full duplex mode. Configure in full duplex communication. So to do that, you need to set the bit 10th bit as 0. So if we go here, the 10th bit, RX only. If you go bit 15, 14, 13, 12, 11, and if you go to 10, if you want to use as full duplex, that is both transmit and receive, you need to set this 10th bit as 0. So that's what we're going to do next step. 10th bit as 0. So we need to copy this, Control-C, Control-V, and then change this to bit 10. Then you need to set the master bit, which is bit number 2, master. Because this is SPI, you're going to control one master to slave, so you need to set bit 2 as 1. Set bit 2 as 1. For that, you just copy this, come here and paste it and change this to 2. Okay. After you set that as a master, then make sure you need to transmit MSB, transmit MSB bit, most significant bit, and set this. Because in the register it has got only LSB first, so bit 7, if you come to bit 7, to make this as MSB transmitted first, you need to make this bit 7 as 0. So that's what we're going to do. Bit 7 as 0, so again you copy the SPI 1 to transmit MSB first, then change this to bit 7, MSB first. And after you transmit MSB first, then you need to configure data as 8-bit mode. So you got to use the data frame format, and that's on bit 11. Go back to the register, bit 11. If you see data format, if you want to use this, you need to set this as 0 bit DFF. Here bit 11, you need to set that as 0. So again copy this and change this to 11. 7 and then 11. After the 8-bit mode chosen, then you need to select the software, select software slave management bit So to do that, you need the internal slave select and also the slave select management. So that's bits 8 and 9 you need to set, these two bits 8 and 9. So go back, you need to set, so we need just the R, copy this, and this will be 8th bit and this will be 9th bit, it's the same. So after selecting that, then the final step is the SPI enable, SPI 1 enable. So to do that, SPI 1 enable is a 6th bit, as if you remember, if you come to 6th bit, SPE bit 6, you need to just SPI enable. If you set as 0, then that means it's disabled. If you set this bit as 1, that means its peripheral is enabled. So that's the step. Control C, Control V, and this is bit 6. So we have configured all the necessary pins that we need. That's well and good. So save and do a right click and check for any errors at this stage. 0 errors, 0 warnings, that's really good. So now the next step, you got to write the chip select enable. So you need to also use the chip select for it to enable and disable, and that's very simple. So after config, I will create 2 more functions for chip select enable and disable. Copy this, paste it, chip select. One will be chip select enable and the other will be chip select disable. And then write a function for enable first. So copy this, come down, so in order to enable the chip select, you need to enable the output data register. That's if you go to ODR register, output data register, this is alternate function. Okay, it's better go by the contents, so we need to go to GPIO registers. GPIO registers, you need to go to output data register. That's a port output data register, ODR. That's the output data register. You need to, because we're using PA9, so that's the bit 9, so you need to use this bit. So I need to just set this bit because that's a GPIO bit. That's why it's easy. So GPIO A, and set the output data enable is, you got to negate that. Negate 1U, sorry, 1U9. Okay, and next function is the disable function. Disable is the opposite, so I need to just set void CS disable. You got to just set this bit. Yeah, so we have written the program for now. I will go and save and do a check. Okay, 0 errors and 0 warnings, which is a good sign. With this, the initialization part coding is done, and we also did SPI configuration, also CS enable and CS disable. The rest we will see in the second part. So far we covered all of this and it's all working okay. So with this I conclude this session. I will go back here and finish off for the day. So what we learned today so far, you learned about the SPI and all the basic fundamentals of the SPI, and also you learned about how the timing diagram works, and also you went and learned about how the SPI work. So as I keep saying, you got to also build your mindset as well when you develop your skill set. And I would like to bring this to you today by the famous Willie Nelson once said, get rid of the negative thoughts as soon as you get that in the mind, immediately discard that. Otherwise that will lead to only thinking about negative terms. Instead, change the negative thoughts with the positive ones and you will have positive results. So always be positive and everything will be positive. No matter what happened in the past, don't dwell on the past. Past will make you to learn the lesson. So take that, whatever the past lesson has taught you, and replace that to the present and the future, so you know what to do and where to go, what to hit to achieve your goals. So please change all your negative thoughts to positive thoughts and all the positive things will start to happen. And please don't forget about the involvement, the top 10 goals, and write your top 10 ideas to achieve your goals. And please at least spend 30 minutes to do some exercise, and please spend 15 minutes to do some meditation just to free off your mind, and 10 minutes to actually visualize that you achieved those goals, and another 10 minutes to plan for the rest of the day activities, and 2 hours you get 2 points for learning and capturing the notes. Please do post all your achievements in the Facebook group. This will help each other as we are helping each other out, and this will motivate us, and we'll be able to learn everything as a group. And there is combo internship coming up. I don't want to put everything in one single course, so I divided it into 3 different courses. To get the full experience of Cortex M4, please do purchase the beginner, intermediate and the advanced course. And also please stay tuned with us. These courses are in progress and you will be the first person to know, and when it is ready you can enroll to them and update your skills accordingly. I take this opportunity to thank each and every one of you to be with me to learn another communication protocol on part 1. Please go and enjoy that deserving break from the screen. This is Arul and Bukarasu. I am signing off on behalf of A2DG. Huru for now. I'll catch you in the next session. Until then, take care. Catch you later.